Has it detected? No, it's not. It should be green. Can you hear? Good. Okay, a very good morning, Happy New Year, and welcome to year 17 of Chayanwa. So, for those who are coming by chance for the first time, Chayanwa happens on the first Sunday of every month over here at Prithvi Theatre. The third Sunday, Ruparel College. That venue might change, we will keep you posted. And if a month has a fifth Sunday, it's a live from a lab in the IFR. And we try to get you some aspect of science, mathematics, engineering, whatever it is that happens connected to TIFR, which is for the general public. And we've been live for the last few years as well, since we now know how to do it after COVID. Though the question answer session will be only for us over here, we can take a few questions from the live session as well. On that note, it's a pleasure to welcome Professor Subir Sarkar. Can you hear? Because Subir, I'm on your mic.
Oh,
so you should be here.
I should be there. All right.
I don't know why that's not green, but anyway, it's okay.
It seems to be picking up.
Seems to be picking up. It's fine. The first session is very special. Now, usually you've always seen it as a researcher from TIFR, but we have a special person who has a very, very strong TIFR connection. Subir Sarkar is a very distinguished physicist from Oxford University, the Department of Physics, where he is an emeritus professor right now. But Subir started his career at IIT Kharagpur, and then he did his PhD in TIFR, was at TIFR for a while, dabbled in all kinds of theoretical physics, but also in trying to get science education across the country through Ekalavya and forums like that. After which he has been in Oxford for most of his career as a high energy particle astrophysics cosmologist, whatever that part, I think he will tell you better. He has been associated with the Department of Theoretical Physics in TIFR as an adjunct member for several years. Right now, he is visiting us under the Bhabha DST scheme that allows people outside to spend time at TIFR. And it's always a pleasure to see Subir at TIFR, and it was very kind of him to agree to give our special, the first session of 2025. So please welcome Subir. Now, online audience, please put your questions in the chat. I will monitor the chat on the phone. If it's important enough, I will interrupt you and ask. If not, we will take questions at the end. And then after the chai break, we will have much more questions as well. Audience over here, if you have a question, please raise your hand. He'll try his best to think. Please repeat the question for the online audience. And on that note, let's now share screen before we forget and get started. Okay.
Am I sharing already?
No, you're not. You have to start this.
Left it as it was. Now I have to share it here. Okay?
Yeah.
Full screen. Yeah. Okay. Oh. Just drag it here. Pause.
Yeah, you're fine. This is what we see.
Okay, excellent. So thank you, Arnab, for that kind introduction, and good morning to all of you. It's good to see so many of you here on a nice Sunday morning. So today's topic is going to be cosmology. That's the science of the universe. But if you were to ask a sociologist or an anthropologist, they have a wider interpretation of this word, in the sense that for them, every culture in history has had its cosmology, which is their way of trying to make sense of where we are and often of how we ought to behave in relation to our environment. So, the anthropological people will tell you that, say, the Aboriginals of Australia, they have a 40,000-year-old cosmology called the dream time, which actually is a prescription for how they conduct their lives as well. But today we are going to talk about physical cosmology, which is modern cosmology, where we are observers, objective observers. The universe speaks to us, we record, but we try to understand and interpret it in terms of the laws of physics, which we study in the laboratory. Right? So in that respect, we are not participants in the universe. We are simply the recorders. And that philosophy is rather well captured, I think, by this ancient symbol that you see here. This is called the Ouroboros, the snake swallowing its tail. And what this is meant to illustrate for you is that our present model of the universe is based on the belief that the laws that we determine to be the what governs the dynamics of all systems that we know actually also determines the structure of the universe as a whole. So here you see the larger scales in the universe going down to, we are in the middle, and then down to the smaller scales in the universe. And the idea is that these laws of physics on the most short scales actually determine the structure of the universe on the largest ones. Now, this is a logarithmic scale, which means it's in powers of 10. And here we are, this is 1 centimeters, this is 10 to the 5, 10 to the 10, 15, 10 to the 20, 10 to the 30. So we are going towards the biggest scales through the solar system, galaxies, clusters, superclusters, and so on. Whereas the other direction, we are going down through, bacteria, paramecium, atoms, the fundamental particles that mediate the interactions that we know, weak and strong interactions, and down to even shorter scales where there are question marks, because we have only explored in the laboratory down to about this scale, 10 to the minus 18 centimeters. That's the smallest scales to which we can look using machines such as the Large Hadron Collider we have at CERN. Beyond that, we need to speculate about what the laws of physics are, but we know that there must be new laws of physics there, because they would have accounted for the fact that in this universe, we have more matter than antimatter. That is not in the current physical standard model that we have. We have something called dark matter, which is very likely a new particle, a relic of the Big Bang, that must arise in new physics. There are little fluctuations in the universe that grow into this huge structure that you see there. And I'll tell you about all this as we proceed through the talk. But the real point that I want you to take away from this picture is that the reason we think that the fundamental laws of physics control the universe as a whole is essentially because the entire universe and all it contains, we seriously think, was once smaller than the smallest thing you can think of, smaller than a nucleus. And this is something that is based on observations. This is not philosophy, but I'll take you through the history of how we came to this conclusion in the time available. So we'll start by asking a very simple question, and that was going to be, sorry? Okay, sorry. I have to get my glasses on to see it. Yeah, just please do it. Yeah. That you have to drag. Yeah, just put it there, that'll do, yeah. So a question that would have occurred to all of our ancestors, wherever they were, I've taken an example from Greece simply because they documented things and we have those records so we can ascribe names to sayings, is there an edge to the universe? So, I said that we are just observers. We do not react to the universe in the way that ancient cultures did. But nonetheless, I think all of you who have ever gone out and looked at the dark night sky would have felt the same sense of awe and wonder that our predecessors did. And we would naturally think, if you look out at the universe, does it go on without end, or is there a limit to it? Now, the Greeks were, of course, a martial nation, and this gentleman, Archytas of Tarentum, actually pose this as a military question. If I chuck a spear across the edge of the universe, wherever it is, what will happen to it? So there are three possibilities, and three schools of philosophy sprang up in order to respond to those. So one possibility is that, oops, I'm sorry. I see. Thank you. Yeah. Yes. So one school of thought was that there is a cliff at the edge of the universe, as you see up here. That was the Aristotelian school. Another school said there was this is a wall at the edge of the universe. The Stoic school held that there was a cliff at the edge of the universe. And then there was an intermediate school that said, well, there's a marsh at the edge of the universe. It's neither one nor the other. I'm saying this to simply illustrate that there's only so far you can go with just talking about things, right? Because none of these groups had any way to demonstrate the correctness or otherwise of their belief, right? And so things proceeded till the Middle Ages. Now it's 2000 years later. In medieval cosmology in Europe, there was for a long time this system which held sway for 2000 years, going back to Aristotle and Ptolemy and so on, in which we are at the center of the universe, and the known planets and the moon and the sun, of course, they all orbit around us. So you can see the planets here going up to Saturn. And then there is this, what they call the crystalline sphere, the primum mobile, of fixed stars. The stars don't move on the sky. All the planets and the moon and the sun do. And this actually is a pretty good representation of what we would see when we look out at the night sky. That's how it looks to us. So this is not a bad model. It had, of course, no dynamical basis. And it's interesting, this picture, which I've taken from a famous sort of road movie, if you can call it, the Divine Comedy. Dante Alighieri goes to the universe led by his muse Beatrice, and he records what he sees. And he actually says something interesting. He says, beyond the fixed sphere of the stars, there are converging rays of light ending in an orb of fire. And as you will see later, this is just a teaser. That's actually a pretty good description of our modern view of the cosmic microwave background, but we'll see how that comes about. So fast forward another few centuries, and we come to the Copernican revolution, which was recorded in this book that Nicholas Copernicus wrote in 1543. You see, the only thing that has happened is that the sun and the earth have interchanged places, right? Everything else is as before. The planets are going around in circles. There is the crystalline sphere of the fixed stars. But this change, of course, was quite profound philosophically. We are no longer at the center of the universe. And this is why the Copernican revolution is rightly regarded as one of the major changes in our outlook on the universe. Interestingly, for those who are interested in the history of science, this had actually been anticipated quite a long time ago, 2000 years before Copernicus. This gentleman here, Aristarchus of Samos, he in fact had already speculated that the stars and the sun remain motionless, that the earth revolves around the sun in the circumference of a circle. And this is recorded by no other than Archimedes, who was actually on sabbatical at the great library in Alexandria. That's where Aristarchus was based. So that's how he knew about it. And this is something quite interesting, because to me as a physicist, what is interesting is how could Aristarchus possibly have guessed that? He didn't have any observations. So we'll see how he did later. But, it's worth studying the history of science, because it is often completely counter to all one's received notions about who did what to who. In fact, there is a kind of a folklore theorem in physics that things are usually named after the person who didn't discover them. But, that's actually an important point, because that highlights the fact that, without kind of laying too much of stress on this, we do things for the pleasure of finding things out. It's not really to get our name onto stuff. It doesn't really matter whose name is on it. But the point is that in spite of all those advances, we still thought, this is now still the Middle Ages. We are now talking about this picture, for example, is drawn in the mid-19th century, that space is finite and it has an edge. And that raises this conundrum, this pilgrim who's got his head stuck at the edge of the universe. Is he in the universe or is he out of it? I mean, the universe is everything that there is. So how can you have an edge to the universe? And in fact, Kant, the philosopher, he posed this as an antinomy, as a contradiction, which was that if you had these three statements, space is finite and homogeneous and obeys the laws of Euclidean geometry, he could prove logically that all three assumptions can't be true at once. As you will see later, what actually gave way was the laws of Euclidean geometry. We graduated to the geometry of curved spacetime. But let me continue the historical narrative. The first person to actually kind of take the gauntlet and say, look, enough is enough. Let's not mess around with this finite edge of the universe. The universe is infinite. Ho gaya. And you see the fixed sphere of the crystalline sphere of the stars has now been dissolved into a star stretching out forever. And in fact, his entire paper is written on the outside of this picture. Those days, papers were very short. Okay? And what I find interesting is that at that time, this is 1576, there was a lot of interplay and communication between artists, writers, scientists, etc. And Shakespeare scholars point out that, for example, this debate as to the finiteness or infiniteness of the universe is in fact recorded in his plays. So Hamlet says, I could be bounded in a nutshell and count myself a king of infinite space. He is in fact referring to this very debate that was then raging as to the finiteness or infiniteness of the universe. However, there is a problem, and that is what I'm going to talk to you about, because that's where physics enters, measurements enter. So Johannes Kepler said, if this is true, and there are other suns which are similar to our sun, why don't they collectively outshine our sun in brilliance? He says, our world does not belong to an undifferentiated swarm of countless others. There can't be infinite number of stars out there. Otherwise, the whole celestial vault would be as luminous as the sun. Remember this phrase, because we'll now show you in detail how that arises and that Kepler got it right, right? This much later came to be called Olbers paradox, illustrating the point I just made, that things are usually named after people who had nothing to do with it initially. Kepler, in fact, came up with Olbers paradox. But those days, as you know, there was no internet. It took 120 years for Edmund Halley in Oxford to hear about this. And he actually gave the wrong answer to this question. He gave the same answer that if you ask somebody on the street, you know, there are all these infinite number of stars out there and they should be, you know, covering the sky and blinding us. Why isn't that so? And they would say, oh, come on, don't be silly. These stars are so far away. They must be all shrinking to tiny little points. They can't cover the sky. And that's just what he said. Those far short of the remotest vanish even in the nicest telescopes by reason of their extreme minuteness, so that they are not sufficient to move our sense. Now, this is what an ordinary man could have answered, and they would have been right in the sense that that is the instinctive answer. But Halley actually had a responsibility to read the book that his friend Isaac Newton had just published with his financial backing. He paid for the Principia Mathematica to be published. And Isaac Newton had just come up with something called calculus. And the point is that the stars, if I take a disk and I take it further and further away from you, it does get smaller and smaller. But the number of objects at a given distance r increases in exactly the same proportion. So these two factors should cancel, and actually it should not matter what the distance is. And to illustrate that, let me show you a simple diagram. This is the only bit of maths we are going to have in this talk. So consider that we are here and we construct shells around us, and these are full of stars. The number of stars per unit volume is capital N. What is the volume of one of these shells? It's 4 pi r squared, the area, times the width of the shell, which is delta r. So that's the number of stars in the shell. But each star here, the amount of light from it that falls on the Earth is the amount of light it is putting out, L, divided by 4 pi r squared, right? This is in the usual three-dimensional space. So you see this 4 pi r squared and that 4 pi r squared cancel out, and you get exactly the same amount of light from each shell. So if you had infinite number of shells, you'd get an infinitely bright sky. But in fact, Kepler was right. You should not double count. So in any given direction, if I see a star, I should not then consider all the stars behind it. I've been blinded already. I don't need to overdo it. So the conclusion is that the sky should be fully covered by stars. In every direction I look, however far away, there should be a star blocking my line of sight, just as Kepler said. And that is 10 to the 14 times brighter than reality. 10 to the 14 is a huge number, right? That's 100 million times brighter than what we actually see on the sky. Now, this is something that we cannot ignore. It is a problem, and astronomers took it seriously. This Swiss astronomer suggested that the answer might be that the power of light diminishes in greater proportion than the inverse square of the distances. He was ahead of his time. That does happen, but in higher dimensional spaces. In the three-dimensional space we live in, it is the R-square law, as you know. Or that, in fact, the light is absorbed by some fluid capable of intercepting light. He's just saying maybe there's a kind of a dust or something between the stars, and that absorbs the light. And that is something that is natural enough to suggest. However, subsequently, Lord Kelvin and others developed the science of thermodynamics. And what that tells you is that once you put out heat, it's got to go somewhere. So imagine you are sitting in front of a roaring fire and you got that metal grill in front of you to dull the heat a bit. If you leave it there long enough, that grill is going to get just as hot and radiate itself, right? So the dust is going to heat up and also radiate the light. You can't just get rid of it. Of course, there is a time scale involved here. You'll have to show that it happens within the lifetime of the universe, but that indeed is true. So that is not an answer. And in fact, to illustrate to you in kind of simple terms that what you're talking about is not just a mathematical trick, this is something that you have all experienced. When walking in a forest, we can't look through the forest if the forest is infinitely long. And this was a popularizer of science in the 17th century who gave this analogy. So, for example, consider this to be the sun tree. We are standing here and we kind of turn round and round every day and we see it, half the day and then it's night. But even when I've turned away from the sun tree, there are all these other stars there and I can see them, just as I can see all these other trees. And if I paint the trees white, I should see a wall of white. So this should kind of convince you that there is a problem. This is in 2 dimensions, but all you are doing is generalizing it to 3 dimensions. Now, one thing I would point out here, I can see a little bit of way through the forest, but there is a wall of trees at a certain distance. In technical terms, you would say that we use a term in physics called optical depth. What is the probability of scattering? And that optical depth becomes 1, which means there is a probability of my sight being blocked, which goes up to 1 here. Here it is less than 1. There is some chance of my looking through the trees. But there is a wall of trees. Keep that in mind for the future. Because that wall of trees or wall of stars doesn't appear to be there on the real sky. This is what the real sky looks like. This is the Milky Way. This is Sagittarius constellation. There in the center is the massive black hole of our galaxy, which is fortunately not feeding. It is quiescent for at least a few million years. And we can see this lane of dust and stars, that is the Milky Way, amazing sight on a dark night. But I can look out to the rest of the universe. The stars are not actually covering the whole sky. I'm not being blinded by stars any direction I look. And this is the famous Olbers paradox, which finally was formulated by this gentleman in the 19th century. But actually, he missed the trick. The real question is, why is the sky so dark in the day? We see only one little sun there. The rest of the sky is empty. Where are all the stars that should be covering that space? So now let's get real. So far, we have been showing pictures. What I want to do is, in this talk, show you one calculation and demonstrate that's how physics progresses, through making measurements and calculating numbers, so that we don't need to just philosophize about things. We can answer questions that are correctly posed. So the question is, how far can you look in a forest before you see a wall of trees? So if you ask a physicist, he would say, well, you want me to calculate something with the dimension of a length. what are the two parameters in the problem? One is the number of trees per unit area, and the other is the width of the tree. If the trees are very big, then of course there is more chance that they will block my sight. So the distance I can look out must be inversely as that, right? And if the trees are planted closer together, if n is a large number, then I can look out less distance. So that must also be in the denominator. And in fact, this does give you the dimension of a distance. So, you can work it out by geometry or just by dimensional analysis. And in fact, if you just plug in some numbers, if you say that this R is 1 meter or so, and the trees are, say, spaced 50 meters apart, one here, one at the back of the hall, then typically, according to this formula, you should be able to look out for about a kilometer. And that does correspond to our experience. We have been in forests. We know how far we can look. So what about the stars? Let's generalize this to 3 dimensions. So each star is like a disk of area pi r square, where r is the radius of the star, and that covers pi r square of the sky. And the number of stars per unit volume, let's say, is capital N. So the lookout limit for stars, in analogy to this, would be 1 over pi r squared times capital N. That also has the dimension of a distance. And now comes the rub. What is capital R and what is capital N? How big are the stars? How far apart are they? We can't tell that by just looking at the sky. They're just little pinpricks of light projected on the sphere. So now we have to learn to measure things, and that is the subject for the next 20 minutes, how we learn to measure the universe. So the story starts, again, pick the Greeks, but this was happening in many cultures at the same time. In the Mayans were doing it, Mesopotamians were doing it, ancient Indians were doing it, Chinese, anybody around the time. But this guy left records. So you know that he was the librarian at Alexandria, where the great library is, and he read that on Midsummer's Day, which is 22nd June, that there was a well at a place called Siene, Aswan today, where there is a big dam, as you know, where you could see the bottom of the well only at noon on Midsummer's Day. What that means is that the sun is exactly overhead at that point. But when he walked out in Alexandria and he stuck a stick into the ground, they called it a gnomon, that stick cast a shadow. And he measured the angle of that shadow to be 7.5 degrees, assuming that the light from the sun came in parallel lines. So if Alexandria is 800 kilometers due north of Aswan, and the angle is 7.5 degrees, then it is simple to work out what is the distance you have to go to make it 360 degrees. That is 40,000 kilometers. Now you might ask, how did he know it was 800 kilometers? Because he asked the soldiers. When they marched, they kept track of how long they had marched, and they measured it in stadia, the length of a stadium. So they had marched 5,000 stadia, and his estimate of what that corresponded to in miles was right, 500 miles, 800 kilometers. And Archimedes had already worked out the value of pi, and so he knew the radius of the Earth. This is a pretty precise number, given that he was doing this in 235 BC. And people knew that the Earth is round. All that stuff you hear about Columbus didn't know that the Earth was round and he thought he would follow. It's all nonsense. There were actually maps of the world in circulation in the universities along the Silk Route, etc., long before that. Anyway, let's move on to the next state of affairs, which is measuring the distance to the moon. Now, again comes Aristarchus, the other guy, and he says, look, if I take a little coin and I hold it up with my hand, I can just about eclipse the moon. And the size of this coin in ratio to the length of my arm, it's 110 times smaller. So therefore, the size of the moon in ratio to the distance of the moon is also a factor of 110, right? And he also observed that if you look at eclipses, when there is a solar eclipse, the shadow of the moon, which is between us and the sun, just about hits the Earth. The eclipse is over very quickly. The shadow sweeps across. But when it's a lunar eclipse, when the moon is in the shadow of the Earth, then it takes a lot longer. So he constructed this trigonometrical problem from which you can work out that the Earth's diameter is about 3.5 times the moon's diameter. Right? I'll leave this to you as a homework exercise to do. Right? He did it in 230 BC, you should be able to do it. And then, since I told you that the distance is 110 times its diameter, it's 30 times the Earth's diameter, that's 400,000 kilometers. So we have already made a lot of progress, but now we need to know the distance to the sun. Now that is tricky, because although you're smart enough to deduce that when the moon is exactly half full, it must be a right-angled triangle between the Earth, the sun, and the moon. So all you need to do, since you know this distance already, is to measure that angle. But that's more easily said than done, because it's a very small angle. And he didn't have any tools. So he guessed this was 3 degrees, this little angle here. And so he thought that the sun is 20 times further than the moon. But he was wrong by a factor of 20. It's actually that angle is only 10 minutes of arc. It's 1/6 of a degree. So the sun is actually 400 times further. And that's such a long distance that we start measuring it not in millions of kilometers, but we talk about how long does light take to cross the distance. And light takes about 8 and something minutes to cross that, 500 seconds. So we now know that since the sun's also subtends half a degree on the sky, same as the moon, totally by accident, but its diameter therefore is 1.5 million kilometers. So we have our first number. We wanted to know how big stars are. Well, they're about a few light seconds across, right? And actually, to measure the distance to the sun, we had to wait till the 17th century for the transit of Venus, which some of you might remember happened now, I don't know, 10, 15, maybe 20 years ago. It doesn't happen often, but I watched the last one. You could see the disk of Venus going across the surface of the sun. And this gentleman, Jeremiah Horrocks, after whom a university is now named in Lancaster, he measured that, and he worked out that the sun's disk is 33 times bigger than the Venus disk, but Venus is about 3.5 times closer, because he also worked out by trigonometry that the maximum angle between Venus and the sun is 45 degrees. So this distance between sun and Venus and sun and Earth, that ratio must be 1/√2. It's basic trigonometry. Only thing is that he had to assume something about the intrinsic size of Venus. He said it's about as big as the Earth. Actually, it turns out that is more or less true. So we now know the sun's distance, but we had to wait till the 17th century to know the distance to the sun. It's 150 million kilometers, like I said, 500 light seconds. So now let's get a sense of the scale of things. Here we are. You know, these are the minor planets, Mars and Mercury and Pluto, which is not even a planet these days. Venus is, as I said, roughly the same size as the Earth. But compare ourselves to the gas giants, to Uranus and Neptune and Saturn. We are tiny. We are nothing. We are like little dots there. And then if I put the sun there, I mean, we are just completely negligible. The sun is huge. It's the major player in the solar system. We are just little test particles orbiting around it. And the nearest star, Proxima Centauri, which is like our sun, is 300,000 times further away. The universe is very, very dilute. Everything is really spread out, right? How do we know that star is so far away? Because there is this phenomenon called parallax. So you see, as we move around in our orbit around the sun, so we are crossing a distance of 186 million miles between June and December. And you can see that the picture of the sky, so this should be an animation. It is, yeah. So it slowly moves across the sky, right? And in fact, from here, the star looks in this direction. From here, it looks in that direction. And this was first measured for a star by the mathematician Bessel. You know, those days people didn't say to themselves, you know, I'm a theorist, I should just do theory. I'm an experimentalist, I should just do experiment. They did everything they could because they had intellectual inquiry. These days, we are far too specialized. We ought to break out of that. Now, this satellite Hipparchus, launched by the European Space Agency, it could measure angles down to 1,000th of an arcsecond. Because if you measure 1 arcsecond, then the distance of that star is 3.3 light years, which in astronomy we call a parsec. So we can look up to 1,000 parsecs, a kiloparsec with Hipparchus. But this satellite, which is currently in orbit, is now measuring it down to about 1,000 times more precisely than that. So we can look through our entire galaxy, which is about 10 kiloparsecs across, and measure the distance of every star in our galaxy. And Gaia is in the process of doing that. It's also measuring their velocities by the Doppler shift. So it's constructing what in physics we call the six-dimensional phase space, velocity and distance. And therefore, once we have that, you know what, we can run that movie backwards and we can work out how our galaxy formed. The old Deus Ex Machina dream of the Victorians will actually come true. So you have to go further, however. This is just the nearest star. And to do that, we need standard candles. What that means is that if I am standing here holding a 100-watt bulb, and I tell you it's a 100-watt bulb, then if I stand twice as far away, that will look dimmer. And you will know that I'm further away because you know that I'm holding a 100-watt bulb. You know how much light I'm putting out. Now, nature has kindly provided us 100-watt bulbs or objects whose absolute luminosity can be determined by measuring some other property that is quite obvious. So, for example, there are these stars called Cepheid variables, so called because they were first found in the constellation of Cephus. And here is one of them. You see its brightness varies like that. This is over a period of days. And you can see, not very well here, but the star brightness is varying up and down. And what that means is that we can use that to calibrate the luminosity. If I just measure the period of variation, from that I can read off what the absolute luminosity of the star is. And what happened in 1923 is that Edwin Hubble found such a Cepheid variable on the outskirts, where he has marked it as VAR, of the Andromeda Nebula. The Andromeda Nebula was thought to be a blob of gas, in our Milky Way. And he suddenly finds a Cepheid variable there and realizes that it is not in our Milky Way at all. Andromeda is much, much further away. The reason he could therefore discover this was due to this lady. She was the one who had developed that Cepheid calibration technique. She is not as well known as Hubble, but without her, he could not have made that momentous discovery, which is that Andromeda is not just a cloud in our own Milky Way, it's a galaxy like ours. The world suddenly became a lot bigger, because every one of those little bits of light that you see up in the sky is another galaxy like ours. This is what Andromeda looks like, very much like our own galaxy. It also has satellite galaxies, like we have the Large Magellanic Cloud and the Small Magellanic Cloud. But it is 2.2 million light years away from us. So in our own galaxy, we live out in the suburbs like Bandra, we live out here, much like the Prithvi Theatre, right? So to do this, we need bigger machines, bigger telescopes. And the Hubble Space Telescope, which has just been retired, did fantastic work on this, because it could actually identify Cepheids in galaxies much further away than Andromeda. Here is a Cepheid on the outskirts of this galaxy M100. M100 is 54 million light years away. Looks very much like our galaxy. And if you wait a while, in 2006, a supernova went off in this galaxy here. A supernova is a star that explodes. And here is, again, I hope this animation will work. You see, the star got brighter and brighter, and then it decays. That bit at the end there is the light curve powered by the decay of radioactive nickel-56. It's like a giant thermonuclear bomb as big as our sun. And it blows up in the matter of days, and then it fades. And the extent to which it becomes bright is the same. The physics is the same everywhere. And in fact, a project that was then started back in the late 90s could identify this supernovae anywhere in the universe. So using supernovae as standard candles, we can now look across the entire universe. So I've given you a very brief recap of how we actually did this. But now let's go back to the question we asked. How far must we look to see this bright sky, this wall of stars that should be blinding us? Now we have these numbers. R is, as I said, about 5 light seconds. And the separation between stars, if you take account of the fact that they are mostly in galaxies, and so you have to have a geometric mean between the galaxies and interstellar space in our own galaxy, that comes to about 1,000 light years. So if I plug in this number here and this number here, then I work out that to see that wall of stars, we'll have to look out for 10 to the 23 light years. Right? We couldn't have guessed this. We had to make the measurements to determine this. And that means light will take 1 followed by 23 years to arrive at us from that wall of stars. So you might well ask, has the universe actually been around for that long? Has the stars been around for that long? And if not, how old do you think the universe is? Well, we know that the Earth is only about 5 billion years old. And in fact, we can actually date stars also using uranium. Here is a star observed from a very large telescope at Chile. The names we give to big telescopes are not very imaginative. They're things like extremely large telescope and very large telescope, and we are running out of adjectives. So here is the line of uranium in the spectrum of that star, and you see by measuring that, we can work out the abundance compared to what it started with, and from that we can work out that that star is 12.5 billion years old. That's one of the oldest stars that you have found in the universe. The very oldest is about 13. So the universe is not old enough for the stars to have been around long enough for us to block our sight. In other words, the universe is too dilute now. And that is why the universe looks dark. That is why the stars don't cover the sky. There just aren't enough stars to cover the sky. We are dilute. Why we are so dilute, we'll come to in a minute, but that is the reason why the sky is dark at night. And interestingly, this answer was first given not by an astronomer or a physicist, it was given by Edgar Allan Poe. He says, the only mode in which we can comprehend the vistas which our telescopes find would be by supposing the distance of the invisible background to be so immense that no ray from it has yet been able to reach us at all. Again, you might ask, how did he come to that conclusion? So I leave it to you to read that book to try to figure it out. But let's proceed a bit further, because I promised you a bit about modern cosmology, and I see that I have about 10 minutes to go. The guy who actually was in charge of the Hubble Space Telescope, he gets time on it, his own time. And he chose to use that time to look at a tiny patch of sky, which is like about this size, looked at from the back of the room. And he looked at it over and over again for a whole week. And this telescope has a digital camera, I mean, very similar to what you have in your phone, just a bit bigger. And you can co-add the images. And when you do that, the tiny patch of sky turns out to look like this. It's got thousands of galaxies in it, right? You can see the little shapes coming up, right? This is the Hubble ultra deep field. So you can ask, if this little patch has got that many thousands of galaxies, how many galaxies over the whole sky? The answer is that there are about 10,000 million galaxies in the sky. Now we are clearly looking out of this forest of galaxies. You can see the gaps. What is beyond that? Well, first of all, you must recognize that when you look in distance, we look back in time. There is time travel, but only backwards, okay, not forwards. So when you look at the sun, we see it as it was 8 minutes ago. When we look at the Proxima Centauri star, we see it as it was 4 years ago. When we look at the galactic center, 30,000 years ago. Andromeda we see as it was 2 million years ago. And looking further, the Virgo cluster where M100 was, that is 50 million years old. And when we look at these galaxies in the ultra deep field, we are looking back 12 billion years. So we are actually doing time travel. We are like constructing a tunnel in time. And we are seeing the galaxies in that tunnel along at various stages of development from when they first form to where they take their modern shape. So here is a faint blob that absorbs other galaxies, cannibalizes them, starts forming the spiral arms, and here we are, a galaxy like ours. And the second thing to observe about that picture is that these galaxies, the spectra of these galaxies is different from the spectra that we measured in the laboratory. The spectra of distant objects are all shifted towards the red. The same spectral line of silicon or whatever it is will be further to the red. And we call that the redshift. The observed wavelength is longer than the emitted wavelength. And we think initially it was thought this is due to the Doppler effect, just as the sound of an object which is going away from you gets stretched out. This is something we all know if you have heard a train engine doing that. And in fact, Hubble discovered that the recession velocity appears to be proportional to the distance. Now, this plot is a bit scatty, but here is a modern plot, and you can see that the distance Hubble was looking was just this tiny part. Today, we can look a lot further, out to hundreds and hundreds of megaparsecs. And this is what we call the expansion of the universe. Hubble actually never used that word. He never said the universe is expanding. That's a common myth. He said the interpretation of these observations should be left to those qualified to do so. I'll tell you why that it was actually a good statement. So what we can tell is that galaxies equidistant from us are all moving away at the same speed. If they're twice as far, they're moving away twice as fast. So the length of the arrow indicates the velocity. So let's do an exercise. Let's reverse those arrows. Let's turn back the direction of time. So the ones which are twice as far will reach the center at the same time as the ones which are here. And the ones which are 3 times as far were moving 3 times as fast. So they will also reach the center at the same time. And the rate of expansion that we see today is about 70 kilometers per second per megaparsec. So you can see this kilometer and megaparsec cancel out. Both are units of distance. So the inverse of that is a time, unit of time. That's 14 billion years. So this is why we think the entire universe originated in a Big Bang about 14 billion years ago. Here I'm showing the Earth as the center of the universe, but in fact, it was not. Every point in space-time was the center. And this was not an explosion. It was the birth of space-time itself. Now, I'm just saying these words. You can, record them. You may not really quite understand what is meant by that, but I'll come to that in a minute. So here is a cartoon to illustrate to you this apparently non-intuitive fact that every point can be the center, but it is actually quite intuitive. We all know about a sphere. Every point on the sphere is equivalent. So we could be sitting at the North Pole and we see as this sphere expands, all these points are being pulled away from us at a rate which is proportional to the distance as the arrows indicate. And the wavelength of light is being stretched out. And that is what we call the cosmological expansion. But no point on this sphere is special. So we could pick any point and we would see the same phenomenon. We would see the redshift of light. And the Big Bang, therefore, in this picture is the antipodal point of what you would actually call an expanding hypersphere. It's a 4-dimensional sphere, not a 3-dimensional one, right? And essentially, when you go back in space-time, in time, then this thing is getting smaller and smaller and smaller. So you see that we are all ultimately will be in that initial singularity where we believe all of time, space, and matter were created. You can't ask what was there before the Big Bang in this construction. As Stephen Hawking famously said, it's like asking what is north of the North Pole. By construction, there is nothing north of the North Pole. That is our construction. And indeed, again, I mentioned Shakespeare earlier. One of the very fruitful collaborations between art and science was this Dutch artist Escher, who was a friend of the Penrose family. And he constructed these diagrams. You might have seen these impossible diagrams. This one is actually an exact depiction of a universe where you can see these fishes are getting more and more crowded together as you go towards the end. It's just like you're sitting at the North Pole, looking around the Earth at the South Pole, and things at the equator get more and more compressed because light has to come to you only along the planet. Okay, that's why that little singular point can fill your entire sky, and that is what I'm going to show you next. So I refer you to this Escher painting for more detail. So the bottom line is that we have now established that we are an evolving universe. And so if you can look back in time, we should see the universe getting hotter and hotter. If you look through this Hubble Space Telescope, the deep field and beyond, there are no more galaxies, but the universe is actually smaller and smaller because we have crossed the equator. We are going towards that antipodal point of the hypersphere. And it should be more compressed, it should be hotter, and therefore it should become a plasma. It should become ionized, and we can't look through a plasma. So ultimately, we should see a fireball covering the sky. And that is exactly what these two gentlemen saw from the telescope at Bell Labs in Princeton, close to Princeton University. And they got the Nobel Prize for it because they saw that all over the sky, there was the same radiation. except that that radiation is not at optical wavelengths. It has been stretched out by the redshift of the universe to microwave frequencies, the same microwaves that you use in your oven. In fact, the same frequencies that are used for television. In the old days, when you had to tune your television, if you went between channels, about 1% of the static noise that you would get on your television is actually the noise of the Big Bang. Now, this had actually been predicted by two theorists, but that was not taken notice of. Nevertheless, it was established through this discovery that we have had a hot and dense past, and subsequently in the 1990s, this satellite measured the spectrum of the radiation. You can't ask for a better match of theory and experiment. This is precision cosmology. You see an exact match to the Planck spectrum, and that is how we know that alternative models of the universe like the steady state theory are ruled out, because you can't create as good a spectrum as that by any other mechanism than having a hot dense state. So this picture that satellite Kobe took of the sky also got a Nobel Prize for George Smoot, and what it showed is that there are also fluctuations in that temperature, but by only about 1 part in 100,000. Now, this band that you see here is our Milky Way, which also emits radio waves. But what we are interested in is these hot and cold patches, which are almost the same temperature, but not quite. We believe that these are the seeds of structure. This is what has grown to create the structure in our universe. But this picture is not very good. This is like a picture of the Earth where you can't really make out anything. But if I increase the resolution, you can see that actually that is the Earth. You can make out the continents now. So you need an instrument, more expensive of course, but which can do that resolution. And this was the Wilkinson microwave anisotropy probe, which did those measurements. And what turned out as a result of these measurements is that we believe now that these fluctuations that you see there are actually quantum fluctuations. The entire universe, I told you, was smaller than a nucleus. So quantum fluctuations, which we think happen at very, very short scales, were now dominating the entire universe itself. And they have left their imprint on this microwave background, and they are the seeds for the formation of galaxies. And the latest satellite Planck, launched by the European Space Agency, has measured this in exquisite detail. I can discuss this further later, but you can see the beautiful match of theory and the data, which has convinced us that we understand the physics of this. And this is what has established the so-called standard model of cosmology, for which, again, a Nobel Prize was given. And the story, therefore, is that initially we started with the initial singularity about which you know nothing. We postulate that there was an epoch called inflation, during which those fluctuations were created. We also know nothing about it, really. This is where the observations start. We see the imprint of those fluctuations in the microwave background. Then they grow in the dark matter that fills the universe to create structure. The first stars were formed 200 million years later. The JWST telescope is now observing these. And then 14 billion years later, we have our modern universe. So on one page now, we have the creation story to rival the creation stories of other cosmologies. And this is based on physical science. Now, this is have to be very quick about this because I'm out of time. But just to give you a teaser, there is an indication from the supernovae that the rate of expansion of the universe has started to speed up again. I don't have time to discuss this plot, but this is the bottom line. And for this, again, a Nobel Prize was awarded, because in order to have this speed up of the expansion, the universe has to be dominated by a strange kind of matter, which is got repulsive pressure. Ordinary matter, everything is attractive. Gravity pulls things in, things collapse. But this matter makes things expand. And that is called the cosmological constant, or dark energy. And the new cartoon that comes out tells us that the universe has started speeding up, and many, many telescopes and satellites have been observing what is on the sky, and that all supports this picture. And we have this very uncomfortable situation that it has led us to believe that at least 2/3 of the universe is made of this dark energy. Matter is just a tiny sliver of the total. Dark matter is a bit more. But there is no physical understanding at all of why this is so. So we have a description of the universe that matches the observations, but we don't actually understand what this stuff is, because our best theories, the ones that work very well at laboratory and accelerators and so on, that has nothing to say about this. Now, one could look at it two ways. You could be pessimistic about this and say, what the hell, after all these years, you still don't have the answers. But I see it very positively. It means that for all the young people here, there is stuff to do, okay? There are many things to uncover. We have just given you the problem in a way that you can sort. So let me come to the end of my talk. You asked, where is the edge of the universe? This is the edge of the universe. We can't look beyond it because that's where the fog starts. That's where the plasma starts. And as my friend Max Tegmark at MIT says, that it's very frustrating, because if you could just see another 380,000 light years beyond it, we would see the initial singularity. But we can't, because it's blocked by this fog, because we can only see in photons. But that is now. In future, we might be actually able to look back in a different way using gravitational waves. We have now detected gravitational waves in very sensitive detectors from merging black holes and so on. But gravitational waves should also have been created in the first moments of the Big Bang. And in principle, we can detect them. For example, with this satellite or set of satellites orbiting the Earth at a few million kilometers, this will be launched in a few years. And we should be able to see way back beyond the fog that is created by this microwave background back to the earliest moment. So let me leave you now with a reading list, because you might be wondering where all this information came from. I've drawn on these books. Edward Harrison is a distinguished cosmologist, and all that story about Olbers paradox, he's written an essay called The Paradox of Olbers Paradox. That's from there. If you want to know about curved space-time, I can't think of better book than this one here, Poetry of the Universe. Don't be fooled by the title. This gentleman was the Dean of Mathematics at Stanford. It doesn't use too many equations. It has pictures to show you how to project the sphere onto a plane. So all the pictures I've been showing you will notice were like ellipses. Okay, that's a particular kind of projection called a Mollevite projection. The maps that we use on Earth typically are a different projection. It's a Mercator projection that makes Greenland look bigger than Africa. The projections we use are equal area projections. They don't distort the sphere. And if you're interested in learning about the early universe, this book is still a classic, Steven Weinberg's The First 3 Minutes. But this is where I have some, serious news for you. It's all very well showing nice pictures and telling you this is happening, that is happening. If you really want to understand what is happening, I'm sorry, but you'll have to learn tensor calculus, right? There's no option, because the language that we have to understand the universe is mathematics. We are privileged to be able to understand that language, but we cannot understand at all without that language. So as Galileo said, so easy to understand are all truths once they're discovered. The point is in being able to discover them. Thank you.
Thank you so much, Subir. I am sure you have a lot of questions. But we'll take a break for chai and we'll come back and we'll have questions. But let me take a question from the chat. It's probably one you've got many times before. There are two. Are the laws of the physics the same everywhere in the universe? And how do we know that?
We don't know that. We try and experimentally determine if that is the case. But first of all, you are right. It is a big supposition. For example, we look at the spectra of distant quasars.
I mean, out here, the laws of driving in Mumbai are not the same as even if you go to wherever you are from.
No, the laws of driving as encoded in the handbook are exactly the same. Whether people follow them or not is the question, right? So we like to think that atoms are not, they're not sentient beings. They obey the same laws everywhere, wherever they are, right? But in practice, we try to actually determine, in practice, we try to determine, is that it?
Yeah.
Yes, right, thanks. Okay. So we try to determine whether the constants of nature, for example, so most of our laws of physics are based on simple principles of symmetry and certain numbers that are invariant. For example, the speed of light or the fine structure constant. So I could, for example, ask the question, is the fine structure constant the same here as in a galaxy or a quasar far, far, far away? And that is a question I can try to answer experimentally by looking at the spectrum. So fine structure constant, as it says on the can, is about the fine structure of spectral lights. If I measured that in a distant quasar and I find that to be exactly what I get in the laboratory, it gives me confidence that it's the same constant that is operating there. And that is central to the laws of electromagnetism. So I can then be fairly confident that electromagnetism works in the same way at a redshift of 5 as it does here.
And so far, we have not found anything to the contrary.
So far, we have not found it. And also, on a philosophical note, we should ask questions which are falsifiable, So if I just say, oh, we don't know anything about the universe because the laws of physics are different elsewhere, all I can say is, okay, all right, let's go home. There's nothing more to do around here, right? So you see, that's the end of the story. It's not a very fruitful direction of inquiry to do that. But what is fruitful is to ask, could the laws of physics have been changing over time? It's quite possible since the Big Bang. So then we devise experimental tests to look for that. So all we can say is that at least until after a few seconds after the Big Bang, the laws of physics were the same, because the synthesis of helium in the early universe at a few minutes, that's in Weinberg's book, the first 3 minutes, that seemed to have proceeded exactly according to the laws that we understand. So we are quite sure. In the very earliest moments of the Big Bang, anybody's guess, right? But that is exactly where modern research is currently at. We know the limits of our knowledge. That is the point. And the thing is to define that. Thing is to define all the known unknowns, right? We'll leave the unknown unknowns for whoever it was.
Okay, now I know that don't go home. We could shut
Absolutely.
down and go home,
yeah.
But we will certainly go for chai.
Yes.
Online audience, you don't get chai.
That's it. There's no other question.
There is.
Yeah.
Are there parallel universes?
Again, that's one of those undecidable propositions I just mentioned. If you say there are parallel universes, the first question I would ask you is, how do you know that there are parallel universes? So you would say, well, I'm just wondering if there are. The point is, if we can't communicate with them, if we can't experimentally detect their existence, then they might as well exist. It is a completely philosophical question. It has no meaning, right? The question really would be, if there are parallel universes, do they have some impact on what we do in our universe? So in fact, there is a context, there is the many worlds theory of quantum mechanics, where the existence of these parallel universes is meant to have a bearing on measurements we make in this universe. But in fact, as far as I know, for all practical purposes, which is also a phrase that physicists like to use, everything that we measure seems to be exactly according to the laws of quantum mechanics, which is totally independent of how we interpret the measurement process, whether in terms of parallel universes or not. Therefore, if I am going to be a hard-headed reductionist, I would say I don't care if there are parallel universes or not. I know how things are working in the lab. I know how the electrons are flowing. But it is also true, and this is to the questioner, I don't want to give you a hard time, the fact that these questions occurred to us is natural, because we are sentient beings. We think about things that we are not actually capable of answering. But who was it who said, man's reach must exceed his grasp, else what is heaven for? So there you are.
Okay, thank you so much, Subir. Thank you.
Thank you.
And while you may not care about the parallel universe, I think we all care for a cup of chai.
Absolutely, that's in this universe.
So that's in this universe, absolutely. Grab a cup of chai, let's come back.
All right.
I'm sure you have tons of questions.
Yeah.